Warm good morning to all. So today I'm going to take the session on clustering aspects. So before directly going to the topic, so it's part of this topic is part of data analytics. So in the beginning of data analytics, we will be hearing a lot about prescriptive analytics and descriptive analytics, right? So in the case of prescriptive analytics, the next session will be covered. Topics like classification, regression, all these topics will be covered the next session. So those algorithms, will be doing the predictive analytics. So in the case of predictive analytics, we will be having data sets, and we also will be having labeled data set, labeled columns for us to create mathematical models. So even in industry, current industry practices also, they are expecting students to develop predictive as well as descriptive models based on these algorithms, based on machine learning algorithms. They are expecting students to minimum as a student, when you're getting a data set, you should be able to know what kind of algorithm you should be able to apply. So as an learning and development L&D leader, I am also looking to inculcate these kinds of skills. The skills from the industry perspective, the learning gaps are seen in these areas, because whenever the students are getting some data set, they're not able to identify which feature they need to apply all these things. So in predictive analytics, we'll be applying algorithms like classification and regression. And today I will be taking about descriptive analytics. So descriptive analytics is part of unsupervised learning algorithm, where you will be given a data set. As a researcher or as a student, you will be given a data set, and you need to apply the unsupervised model algorithms like clustering. Like clustering is one of the unsupervised learning algorithms. There are several other techniques that you can apply for in the case of unsupervised algorithms. The three most common types of descriptive analytics are association rules, sequence rules, clustering. Let's have a quick look on these three algorithms. First one is association rules. And this one, we are actually trying to detect frequently occurring patterns between items. Hope you all are familiar with this market basket analysis, where we'll be identifying the products which are frequently purchased by customers in a particular context, right? If you are evaluating a number of transactions in that particular context, we will be evaluating the purchase behavior. And we are also using the association rules for detecting words frequently occur in a text document. And also in the university setting, we can also detect what elective courses are frequently chosen by the students. These things are being detected using association rules. That's the first kind of unsupervised learning algorithm. The second one is sequence rules. And in this one, we are trying to detect the sequence of events, like the purchase behavior. Even in this one, we are just identifying the combination of products, right? The first one, the association rules. Even in the market basket analysis, we're trying to understand the purchase behavior in the item counts only, item set only. In the sequence rules, we are trying to understand the purchasing sequence, the sequence with which certain products are being purchased. Okay, so the second one is web pages. The sequence of, even if you're using mobile application or web pages, there is a sequence. There is a common sequence of the nth web page will not be received through some flow. The common workflow will be there. Okay, common sequence of, for example, if there is a 10th web page, and that web page will be accessed through sequence of web pages only. Okay, so those kinds of insights will be, those kinds of predictions or forecasts will be very useful for the designing of web applications also. Even in mobile applications also, the sequence of the navigation, how the users are navigating is very useful. The third, today we will be learning about clustering, and it's basically about detecting homogeneous segments of observations. For example, the differentiating between brands in a marketing portfolio. So once you are given a data set with n number of features or columns, you are supposed to find out, you're supposed to cluster it. Okay. And the second one is the segment customer population for targeted marketing. So these things, no, one of the popular example nowadays nowadays we are commonly hearing is the cluster, the COVID based clusters, right? So you hope you all know, once a COVID case is reported, the person's location, the geographical location, the person's personal details will also be collected by the agency, medical agency, and they will be clustering based on the location, based on the location you're providing. Okay, it will be either it will be based on the pin code you're providing, or it will be based on the GPS coordinate you're providing. Okay, for example, if you're reporting in mobile application, longitude and latitude will be used. So the clustering will be, the grouping will be happening based on those parameters. So now moving to the clustering aspect. So clustering is basically a collection of data objects. And here we can learn about similarity and dissimilarity. Okay, with these two things we can learn. Now, similarity means to one another, similar to one another. The objects in a cluster, in a cluster or related will be related to one another within the same group. And dissimilarity means you can also identify the dissimilarity of objects by using clustering techniques. That is dissimilar to objects in other groups. So in cluster analysis, it is used for finding similarity between data according to the characteristics found in the data and grouping similar data objects into clusters. So a good clustering method will produce high quality clustering. For example, the objects in a particular cluster, if you once you got the outcome from a clustering algorithm, you know, if the two important characteristics should be remembered. That is, the elements in a cluster should have high intra-class similarity. That is cohesive. That is, elements within a cluster should indicate high similarity, cohesive within clusters. And the elements in multiple clusters, the objects or the data points or transactions in different clusters should showcase or should depict inter-class similarity, low inter-class similarity. Okay. So that's all about the quality. How will you evaluate? No, there are if you search in Google, you'll be obtaining any number of clustering algorithms. Okay, even in research point of view, also even there are any number of updations being year by year. There are a lot of clustering updations are being done. So how will you identify the quality of clustering depends upon the similarity measure used by the method, its implementation, and its ability to discover some more hidden patterns. No, so you need to try not one or two algorithms. You need to try n number of clustering algorithms to come up with the best implementations, because it's again depends upon the dataset that you're using, the domain you are going to use. Okay, that the kind of requirement that you're going to, that your research field or your project field will be, that also depends, that also affects the quality of the clustering, the final cluster you're getting. So few applications, more information retrieval, it is used in market basket analysis, city planning, climate, and climate understanding, and land use also. So example, in this one, the input you can see here, the input here is unorganized, right? Even the different kinds of balls are given is from it's easy for us to understand, but from the data set point of view, you will be the columns, the input will be having the Excel format or a row column wise format. So each row will be indicating each of these balls will be the details of each of these balls in the input will be reflected using a single row or single transaction, right? So how will you, the main purpose of this clustering algorithm is to see the pattern. Okay, so it is unsupervised algorithm, and at some point of time, you can check the outcome here. It is the balls, the unorganized input is organized based on the shape. You can, from the output itself, we can easily infer that the clustering, here the clustering algorithm chooses the size, right? And color also. Color is also taken here. For instance, if the size is all same, Then we need the clustering algorithm. We need to give the parameters. How we will see how the parameters are set. And here we can say that color is also one of the primary factor for doing this clustering. Second example you can see here. And the input we are having unorganized objects, and after clustering algorithm, applying clustering algorithm, we will be obtaining organized object clusters. And each cluster you can see here, we are having the elements within each cluster will be showing high cohesive, and the elements in different clusters, the intra-cluster similarity will be low. Okay. Third example you can see here, there's an example of market basket analysis. In this one, you can see here, different objects are just the input is given. Okay, various products are being given and its characteristics are given. And the first one, so three ways it is clustered. The first one is cluster in color. Okay, using the property color or using the characteristics feature color. And you can see here there are 4 different clusters. The second cluster you can see here by shape. It is clustered by using the feature or property shape. Okay, it is evident that the two clusters, we are obtaining 2 clusters here. Now the third one you can see here, if you cluster based on size is again another property. Okay, another feature that is available in our data set. Okay, so it is again the output will be 2. So you can create that. That's why even with a single data set, with the help of single algorithm, you'll be obtaining numerous n number of clustering output. Different kinds of clustering, interesting clustering patterns will be obtained. It all based upon the input you are setting. No, the feature you're selecting. If we, for example, if in this market basket analysis, if you are having hundreds of, just imagine you are having 50 rows, 50 products, and each of the row will be having 10 columns. 10 features are given to you, and you can produce n number of cluster outputs based on your understanding of the domain. Here it is shown only 3 because here again I'm just showing the first one is based on color, the second one is based on the feature shape, the third one is based on the feature size. Likewise, if there are n parameters, you can have minimum, at least you can develop 10 or more than 10 basic clusters, and you can you're trying, if you have the domain knowledge, you can definitely come up with some useful patterns. This is another interesting way of producing clusters. That is, we can group elements. Basically, clustering means we are grouping elements based on the features. No, if you want to group the objects will be having features. So based on the similarity of the features, we are grouping. So in this hierarchical method, you are actually, what we are trying to do is we are trying to understand, at what similarity the objects are showing at certain dissimilarity. For example, B and C. From if initially the 6 given points, 6 data points are given, and B and C at certain points, B and C will be showing high similarity, so they will be grouped here. And certain point D and E, fixed point D and E having that showing some similarity. So we are setting level at that particular level. These 2 clusters are formed. At another level, higher levels, we are setting in some other distance. At that point, B, E, F are showing high similarity, so they will be clustered here. So likewise, we will go through this example in the hierarchical clustering. So hierarchical clustering we can do in 2 ways. That is top-down approach as well as bottom-up approach. So basically, next we are going to see the different kinds of clustering algorithms. The 4 different classifications that I'm going to cover here is partitioning algorithm, hierarchical method. Third one is density-based approach, and fourth one is grid-based method. So first one is partitioning method. In the case of partitioning clustering algorithms, we are actually, if a data set is given, given a data set of n objects, a partitioning method constructs k partitions of the data, where each partition represents a cluster and k is less than or equal to n. Okay, basically say I'm going back to the previous example. That is here, if I'm using partitioning approach, I want to initially set. If I'm using the parameter column, I mentioned that, right? Before running the algorithm, I need to mention that feature, with which I want to cluster it. And I need to mention the number of cluster also. You can see here the number of cluster is 4. Then the second example, you can see here the number of cluster is 2. The example of the third one, you can see the number of cluster is 2. So that the number of cluster you require should be particular. That is again, it's a reflection of number of partitions. The number of, because you are having a cluster, you are given a data set of n objects. And if you're using partitioning, the logic is that you need to partition into k clusters. And the number of the k, the number of cluster k should be less than or equal to the number of objects. So it divides the data into k of groups such that each group must contain at least one object. So typical examples are k-means, k-methods, Clarence. These are all examples for partitioning. In the case of hierarchical methods, we will see one example. The k-means we will see one problem. And then the next type of classification, the next algorithm is clustering algorithm is hierarchical method. So it creates a hierarchical decomposition of the given set of data objects. So hierarchy again is further divided into two. That is a agglomerative approach, bottom-up approach, and divisive approach. Okay, you can see here. This is a example for hierarchical clustering. So in this one, you can cluster in two ways. So agglomerative means you can start from the individual cluster. Here you can see the PQRST. PQRST. These are all these 5 are individual cluster points, and you're actually starting from individual cluster points, and you can merge. Okay, at certain points based on certain merging criterion or distance scale, you can merge. So at this point, SNT level, at this level SNT are merged, at this level PQ are merged, at this level RST are merged. So agglomerative, agglomerative means bottom up approach. Okay, then the second one, hierarchical method, is divisive approach. In the divisive approach, you are actually trying to cover the top down approach. That is, in the case of hierarchical approach, it is divided into agglomerative, that is Agnes, and divisive, that is Diana. Okay, so in the case of divisive approach, we will be having a single cluster consisting of all the elements, and again you will be splitting it based on some splitting criteria. You are splitting it. Okay, you will see some examples. The third kind of clustering algorithm we are going to see is density-based approach. In this, the general idea is to continue growing a given cluster as long as the density in the neighborhood exceeds some threshold. Now, so when we are talking about density-based clustering algorithms, we hear two things: neighborhood and density. Okay, density region. Now, so it is basically the first two algorithms, partitioning as well as hierarchy-based method. So they are all prone to outlier errors. Okay, if a data set contains malicious or some error, malicious or some error transactions, then it will against their calls, the values in that particular columns are very high, meaningless. It will actually mislead our clustering output. Okay, such kinds of clustering will actually mislead the model. So which ultimately we will be getting a few errors in our developed model. Okay, so the density based approach, the one of the main advantage of density based, such kinds of outliers, the outliers are properly handled. And here the method, what they're trying to do is, if you want to run a density based algorithm, you need to give two important inputs along with the data set. For example, in the case of partitioning method, you need to mention along with the feature and data set, you need to mention the number of partition you require. In the case of hierarchical method, you need to mention whether you want Diana or you want to top-down approach or bottom-up approach, and you're giving the data set. Again, you need to mention the splitting and merging criteria. The third one, the density-based approach, you need to mention the minimum radius. Okay, we will see the problem. You need to mention the minimum radius and the number of minimum components or the number of minimum objects in that particular radius. So again, I'm repeating, in the case of density-based approach, along with the data, along with the feature, you need to mention two more details. That is, you need to mention the radius, and that radius actually reflects the neighborhood property. Okay, you are actually indicating that I want, for example, 2 unit or 4 unit of radius, and within the objects within that particular radius will reflect the density of your algorithm. The algorithm is known as the grid-based approach, and in this one, it's we are actually dividing all the objects. We are quantize in this grid-based method, quantize the object space into a finite number of cells that form a grid structure. Okay. So the main advantage of this approach is its fast processing time, which is typically independent of the number of data objects, and it's dependent upon only on the number of cells in each dimension in the context space. So we have one of the examples we're going to see is Sting algorithm. So before starting the clustering algorithms, before the implementation of the partitioning based algorithm, let us have a look into the measures of distance. The distance between two clusters has been computed based on the length of the straight line drawn from one cluster to another. Okay, so it is commonly referred to as Euclidean distance, and in many other distance metrics, many other distance metrics have been also developed, and one of the big, because most of the examples that we are going to see today will be using Euclidean distance. The choice of distance metric should be made based on the theoretical concerns from the domain of study. So again, as I mentioned, based on different areas, the Euclidean distance is one of the fundamental to test and trial, to do the test and trial on various cluster outcomes. There are n number of distance metrics that you need to be aware of, because again, it will affect the quality of the cluster you're going to predict. The distance metric need to define similarity in a way that is sensible to the field of study. So first, we're going to see what is partitioning based method. Suppose you are given a data set D, which which contains n objects or n transactions or n rows. Okay, object in this sense, n rows. For example, if I am giving you a banking data set, each banking data set of 1,000 rows. 1,000 rows means 1,000 transactions you can consider. Each of the row indicates one transaction. Again, it indicates a record or an object in Euclidean space. So partitioning method distribute the objects in D into K clusters. So what we are trying to do is that basically you are getting 1,000 transactions in our example banking example, and I'm trying to cluster it. So basically, an objective function is used to assess the partitioning quality. Eventually, we need to stop it. No, once you run the clustering algorithm, we are using an objective function which is used for assessing the partition quality, so that objects within the cluster are similar to one another, but similar to other objects in other clusters. So the first method, partitioning based method, is again divided into several algorithms. K-means is one of the popular partitioning based method. Okay, and it's basically a centroid based technique. And a centroid based partitioning technique uses a centroid of a cluster, Ci, to represent that cluster. Conceptually, the centroid of a cluster is its center point. You will see in the next diagram what is centroid, or the center of a cluster. The centroid can be defined in various ways, such as by the mean or median of the object assigned to the cluster. The difference between so going to an example here. So this is a one-dimensional example. Suppose that following items need to be clustered. There are, for example, 2, 4, 10, 12, 3, 20, 30, 11, 25. So basically we are having 9 data points here, right? 9 objects or 9 data points. So we are going to cluster these 9 data points based on by using the K-means algorithm. K-means algorithm is one of the popular partitioning based clustering algorithm. So initially, the algorithm will choose the first iteration. The first step, the algorithm randomly chooses. No, I mentioned that one of the important input will be the data set. The data set is having 9 data points here, that is 2 up to 4, 10, 12 up to 25. And we need to, here K is also another input that you need to mention it. Okay, K is equal to 2 here. Now, using K-means clustering algorithm, we are going to run this algorithm. So once the first iteration, since K equal to 2, 2 data points will be randomly chosen. Okay, that is in this one, 12 and 30 will be randomly chosen as the cluster center points. So that is the first step. So the algorithm reads the value of K that we provide, and that much number of data points from the input will be chosen. This is the input here, this first column, and the clusters initially chosen cluster centers are 12 and 30. Okay. So from our data set, initially we are mentioning that, hello. Okay. So once we are giving a data set, and we are also mentioning the number of cluster we require. Here, in this example, we require 2 clusters, that is K equal to 2. So the first step will be it randomly chooses 2 points. Hope you understood. 12 and 30 are chosen as the initial cluster center or centroid. Okay. Now, all these points will be subtracted. The distance from 12 and the distance from, so the initial mean one will be arbitrarily randomly chosen as 12, and the mean 12 will be chosen as 30 here. Okay, right, it will be randomly chosen for the first step. Now the distance from 12 to all the data points will be found out, that is 12 minus 2, 10, 12 minus 4, that is 8, 12 minus 10. That likewise, all the distance from the mean 1, the central 1, 12 to all the data points will be found out initially. The next step, the second random point is 30, right? 30 is chosen as the second random cluster center or mean. Okay, so the distance from 30 to all the data points will be found out. That is 30 minus 2, 28, 30 minus 4, 26, 30 minus 10, 20, likewise 30 minus 25, 5. So in the first iteration, two points are chosen randomly, 12 and 30, and they are considered as the mean or the cluster centers. And the distance, afterwards, if the distance from the mean one, that is 12, to all the data points will be found out, that is 10, 8, 2, 0, 9, 8, 18, 1, 13. And the distance from the mean 2, that is 30, or mean 2, otherwise known as the cluster center or cluster centroid. The distance 30 to all the data points will be found out, that is 28, 26, 28, 18, 20, 18, 27, 10, 0, 90, 5. Now, the final step, the step of the first iteration, each of these data points, basically we are trying to assign each of these data points. 9 data points are given here. Each of these data points we want to assign a cluster number or a cluster label. Okay, that is the intention of a clustering algorithm. Each of the data point that we are giving as input for each of the transaction or a row will be assigned a cluster number. Okay, so here you can see here 2 is nearer to the distance from mean 1 is 10, the distance from mean 2 is 28. So we can infer that the distance from 2 to mean 1 is minimum, that's 10 is minimum. So we can assign it belongs to cluster 1. Cluster likewise 0.4, the data point 4 is near to 0.8, so it is belonging to cluster 1. 0.10, the distance from 0.10 is minimum with mean 1, that is 12. Right, the distance is only 2, so it belongs to cluster 1. Likewise, the cluster 1, we can see 1, 2, 3, 4, 5, 6, 7 data points will be obtained. And in cluster 2, 2 points will be obtained. The 30, the cluster center 30 and 25. So this is the output of the first iteration. So the importance of K is that once you run partitioning based algorithm, here in this example, I'm explaining k-means algorithm. K is very important. That much amount of initial centroids or mean will be randomly chosen, and the distance from those center points to all the points will be calculated, and the minimum point will be chosen for assigning a data point to a cluster. For each of these 9 data points are assigned a cluster number here. Now, at the end of the first iteration, once all the data points are obtained, all the cluster of all data points are obtained, a new mean will be found out. For example, that is, hope you all understood the clustering process. Okay, so in cluster 1, there are 7 points, right? And the rest of the 2 points are assigned to cluster 2. Now, the 7 points in cluster 1, the values, that is 2, 4, 10, 12, 3, 20, and 11. So these points are belonging to cluster number 1, and their mean will be found out. The mean of the data points in one cluster will be found out to obtain the new mean. So the new mean of cluster 1 is 8.85. That is the average or the mean value of the 7 points in the cluster 1. 8.85. Now in the second cluster, what are the components in second cluster? In second cluster, there are 2 objects only, that is 30 and 25. So the mean value is 27.5. So at the end of the beginning of cluster first iteration, two randomly random points are chosen. At the end of the first cluster, the new mean will be evaluated based on the number of elements, based on the components in that particular cluster. I hope this step is clear. So in second iteration, the mean will be the new mean, that is 8.85 and 27.5. These two will be the new centers representing that clusters. That is, mean 1 is 8.85 and mean 2 is 27.5. And again, the same steps will be repeated. All the data points, the distance from all the data points, that is 8.85 minus 2, 8.85 minus 4, 8.85 minus 10. The difference between the distance will be found out. And likewise with mean 2 also, the cluster center 2 also, that is 27.5. The distance from 27 mean to 27.5 with all the data points will be found out. And the minimum distance will be found out, that is a 2. Now the second iteration, the 2 will be, the 2 is close nearest to mean 1. The distance is only 6.85. So again, it will, the label will not change. Okay, 4 is again cluster 1, 10 is again cluster 1, 12 cluster 1, 3 is cluster 1. You can see here previously 20 that is, was belonging to cluster 1, right? Now the second iteration, when we evaluate the difference, when we evaluate the distance using this new means, new centers, cluster centers, you can see here the distance with the first mean, the first cluster center is, distance with first cluster center is 11.15. One minute. Okay, so the second iteration, you can see here the distance with the mean 1 is 11.15 and the distance with mean 2 is 7.5. So the label is changed here. So in the first iteration, the 20 was assigned to cluster number 1, and the second iteration, there's a rearrangement, right? So likewise, few components will be rearranged the following iterations. You can see here there is no change in 30 and 25. Only one, the second iteration, only one element is changed from iteration from cluster 1 to cluster 2. That's the only change. So in this one, there is a slight change. That is, the cluster 1 is having 6 components, 3, 4, 5, 6, and the cluster 2 is having 3 components. That is 20, 30, and 25. So that's a slight change here. And again, the new mean will be found out. Okay, in cluster 1, we are having 6 components, and that new mean with new average will be found out. And in this cluster 2, we are having 3 components, 20, 30, and 25, and new mean will be found out. Okay, hope this is clear. So the clustering, so generally speaking, when we run a partition based algorithm, we provide the data set, we actually fix the features that we want to cluster, and one of the important input should be the number of cluster k. Centroids will be found out. Next, the centroid will be the center points will be randomly chosen first of all, and the distance objects to centroids. No, distance of each object to the centroid will be, or the mean will be found out, and grouping based on minimum distance. Okay, as we expect, and then in the subsequent and in the successive iterations, the elements, the objects will be reassigned to different different clusters based on the minimum distance. Okay, so when will the K-means algorithm stops? Okay, well, what is the stoppage criteria for K-means algorithm, partition based algorithm? So when no object moves in successive iterations, the algorithm takes it as an indication for stoppage criteria. It automatically stops the algorithm, because the further, even if we run n number of times, the elements will not be reassigned, or the cluster means will not change. Okay, once the algorithm identifies the cluster centers are not changing, or the elements are not reassigned into successive iterations, the algorithm stops. So this is an example of one-dimensional algorithm, one-dimensional case, and two-dimensional case also. You can see an example, and in this example, you can see here the data points xy given as xy two-dimensional space, a1 210, a2 25, a3 84, likewise a8. 8 points are given here, 8 data points are given here, and suppose that initial seeds centers. Okay, in some problems like this, you will be given data points. 8 data points are given here, and you will be given the initial seed, that is random. As I mentioned, the first step, the initial senders, or initial senders, sometimes by default it will be randomly chosen. In some cases, you can also arbitrarily mention, if you have the domain knowledge, or if you are aware of the data set, aware of the behavior of your data, then you can say that, for example, in your if the in your assignment mark, if you want to cluster the assignment marks, okay, your particular teacher knows. Okay, for example, the assignment marks varies from 5 to 20. Okay, the maximum mark is 20, and commonly teachers knows then the value of assignments varies from 5 to 20, right? So if a particular teacher want to cluster it, or a particular student want to cluster it, basically we all know the marks will be, again, the cluster centers we can initially set it as 5. If you want 3 clusters, we can initially set the initial seed or the cluster centers as 5, 10 and 15, because if you see the marks, it will be clustered around 5, 10 and 15 commonly, right? So sometimes it will vary from 7, 12 and 17. So if we know that depends upon the characteristics of the students, that the behavior of the variation of the marks in that particular students in that particular subject. So as I mentioned, the domain knowledge is required for arbitrary choosing the cluster centers initially, the initial seed or the initially. If you are well aware of your data sets, the behavior of your data, then you can arbitrarily choose it. That's the first step itself. Otherwise, let the clustering algorithm choose randomly by default. Okay, so in this algorithm, we are arbitrarily choosing. That is the first one is A1, 210. 210 is chosen as the cluster center 1. And for A4, that is 58 is chosen as the cluster center 2. And the third point is A7, 1 and 2 is chosen as the cluster center 3. Okay, the implementation detail and the examples will be again covered by the subsequent in the next sessions. Clustering and hands-on session on clustering, the same examples will be covered. Okay, so in this one, and I just having a quick overview of this example only. In this one, again, all the data points, 8 data points are written here, to 10 to 5, 8, 4, up to 4, 8. 8 is written, 4, 9 is written here. And the distance between, you can check here how the distance is found out. The distance from the A1 to A8 is found out. The distance with the cluster centers with these 8 points are found out using Euclidean distance. Okay, so Euclidean distance means that is x. If the that is xs minus h1 the square plus xw minus w1 the whole square. So that is 2 minus 2 square plus 10 minus 10 the square. Okay, so initially since the points are same, the distance will be 0, and likewise Euclidean distance is applied here for finding the distance between the given data points with the center point. Okay, so the distance are 0, 25, 72, 13, 50, 52, 65, and 5. Likewise, the distance from A1 to A8 with the center point cluster center 2. 5, 8 is shown here, 13, 18, 25, 0, 13, 17. I'm not going to repeat the same steps because this will be covered in the implementation hands-on session on clustering. Same examples will be covered there. And the cluster center 3 here, that is the 1, 2, the distance will be found out. And as I mentioned earlier, at the end of the phase iteration 1 of phase 1, each of the data points A1 to A8, the first column samples or data points or transactions will be given a cluster label. So cluster label is an important outcome that is reflected in the first iteration. So 2, 1, 2, 10, A1 is you can see here it is the distance with the cluster center is 0. The first cluster center 1 is 0, so it is the minimum distance, so it is assigned the cluster 1. So it is because logically speaking it is in cluster 1 itself. 2, 5, the distance with is minimum with cluster 3. You can see here the distance between 2, 5 and cluster center 1 is 25. The distance between 2, 5 and cluster center 2 is 5, 18, and with the cluster center 3 is 10. So 10 is minimum here. So 2, 5, the data point 2, 5 will be assigned to cluster 3 here, because it is showing the minimum distance, it is showing the minimum distance with cluster center 3, that is 1, 2. 10, 10 is the minimum distance. Okay, so it is assigned the cluster label 3. Likewise, all the data points will be assigned a label here. So at the end of the phase 1, you can see here cluster 1 is having only one component, that is the cluster center itself 210, and cluster 2 is having around 1, 2, 3, 4, 5 components. So most of the components are being clustered in cluster 2. Okay, and the third cluster is having the third cluster is having 2 points, 2, 5, and 1, 2. These 2 points are assigned to cluster 3. So at the end of phase 1, the clusters are assigned to 3 clusters at the end of phase 1, and new cluster mean or cluster centers will be found out. Okay, so this the algorithm repeats until there is no changing, there is no rearrangement in cluster labels. So that's all about k-means algorithm. So in the implementation phase, you will be getting the idea about how to choose the initial seed. So what is the importance of the k, all these things. But even if you are not having one important aspect of partition algorithm is that even if you don't have the knowledge of k, k is not, you can choose from an arbitrary values. You can choose a range. Okay, you can vary the value of k from 2 to n. For example, if I am not aware that which value of k is good, there are certain techniques for elbow method and hot score evaluation. No, so there are certain or error evaluation. There are a number of other techniques for you to choose the number of k. That will be covered in the hands-on section. How to choose the value of k if you're new to a particular domain. So the next kind of algorithm I'm going to cover is a hierarchical algorithm. So the first one that we have seen is the partitioning method. That is partitioning. We are actually when a number of data objects are given in a particular data set, you need to partition it. So the number, one of the important parameter is k, the number of partition, along with the features. The second algorithm, hierarchical based method, and again we are actually dividing. So if you are given n data sets, this example, 5 data sets are given here. A, B, C, D, E. 5 data objects are given here. And you can perform the cluster in 2 ways. Top-down approach as well as bottom-up approach. Okay, so first one, I'm going to explain the agglomerative lateness. approach. So agglomerative hierarchy clustering method. The first step, you can see here at the top, step 0. It will be all the data points. The 5 data points are represented as individual clusters. So in Agnes or agglomerative or bottom-up approach, clustering approach, all the data points will be represented as a single cluster. Step one, we'll see the one example, what is the levels. At step 1, we are mentioning a certain distance. Okay, we have some arbitrary distance. And at that distance, we want to know whether any objects at step 1 at certain point, at certain distance, you want to know at that point whether at that point whether these objects are showing similarities. So A and B are showing some similarity at this step 1. So they are grouped, they are merged. Okay, they are merged into one cluster, A and B at step 1. And at step 2, so at some other distance, step 2, and D and E, they are showing some similarity. They will be merged. And at step 3, you can see here, these 3 plus points, that is D and E and C, are showing similar. So they are clustered here. At step 4, you can see here that is a stoppage criteria, because all the points are clustered into one cluster. So that is a stoppage criteria. Or you can also arbitrarily stop. If you want to stop at step 2, you can mention that. You can mention that the distance you are going to mention in that level, you can mention as a stoppage criteria. Now, we can also evaluate hierarchical clustering in the opposite direction, as in top-down approach. That is, initially you will be having a cluster of all the points. So you consider all the data points as single object. Single cluster. A, B, C, D, E. Step 0, you can see here. In the case of divisive approach, that is in top-down approach, Diana. All the Diana stands for divisive analysis. Okay, the Diana stands for divisive analysis. In this hierarchical approach, top-down approach, the first step, the step 0 will be all the data points forms one cluster, and based on, so step 1 means splitting criteria. So the previous one, Agnes, we are mentioning about the merging criterion at particular level, at a particular distance, merge the data points. Here we are mentioning about the step 1, we are mentioning splitting criterion. Split at this point. Step 1, at a particular distance, split. If data points are showing these distance similarity, split it. Okay, at step 1, CDE is split from this main cluster, and at step 2, DE is split from this cluster further. Okay, see, eventually at step 4, that is the stoppage criterion. You can see in the case of divisive analysis, divisive hierarchical clustering method, the last step you can see here, the stoppage criterion will be once all the data points are containing only one data objects, then there is a stoppage criterion. When the leaf nodes, this is again called as leaf node of the divisive hierarchy clustering method. So these two approaches are commonly used in hierarchy methods. So initially, Agnes places each object into a cluster of its own, and the clusters are then merged step by step according to some criterion. For example, clusters C1 and C2 can maybe merged if an object in C1 and an object in C2 form the minimum Euclidean distance between any two objects from different clusters. So we'll go through one example. So in this example, the initially 5 data points are given. That is 7, 10, 20, 28, and 35. So I'm going to apply Agnes hierarchical approach, that is bottom-up approach. So the 5 data points are given. I want to cluster it. So there are 2 ways you can apply it: the single linkage Agnes and the complete linkage Agnes. The case of single linkage Agnes, first you mentioned you find out the distance between the individual data points. The distance between 7 and 10 are 3. The distance between 10 and 20 are 10. Write down the distance between the adjacent points. Okay, fine. Okay, the first step, I forgot to mention the first step. These first step, you should arrange the data points in the increasing order of, okay, in the increasing order, you're supposed to arrange it. First step, algorithm will automatically arrange it. And the second step, we want to find out the distance between the adjacent points. The distance between 7 and 10 is 3. The distance between 10 and 20 is 10. Distance between 20 and 28 is 8. And the distance between 28 and 35 is 7. So this is the first iteration. The distance between, first all the elements, the 5 data points are sorted here, the increasing order. And the distance between the adjacent points are found out. Now, at the end of the first iteration, minimum distance will be evaluated. Here the minimum distance is 3. Okay, here the minimum distance is 3. And these 2 points, that shows the minimum distance 3, and it will be merged to form the single cluster. So 7 and 10 are merged after the first iteration, because so at the end of the first iteration, it shows the distance between 7 and 10 are showing the minimum. Okay, so at the beginning of the second iteration, this is the 4 clusters. We are obtaining 4 clusters. Or we can say that at distance 3, these two at distance 3, these two are merged to form one cluster, and their other points are represented as single clusters. They're not showing any similarities at distance 3. Okay, now again for our distance is found out 7 and 10. The distance between 7 and 10 and 20. You can say there are 2 ways you can find out the distance between 7 and 10. So the cluster 7, 10, and 20. That is so 7, 10. You can see the distance between 7 and 20 is 13. The distance between 10 and 20 is 10. So in the case of single linkage Agnes, the minimum distance will be taken here, because the maximum distance is the maximum distance is obtained between 7 and 20, right? Because they formed a single cluster, the minimum distance will be taken in the case of single linkage. So 10 will be chosen as the distance between the cluster 1, that is 7, 10 with 20, as it is a single linkage approach. The distance with 20, 28 is 8, and distance between 28 and 35 is 7. Same. At the end of the second iteration, the minimum distance is 7. Hope it is understood. So the merging criterion is 7. The level 2 is 7. Okay. So the first at the beginning of third iteration, cluster 1 is will be having 2 components, 7 and 10. Cluster 2 is having 20 only. Cluster 3 will be having the 2 components, 28 and 35. They are merged in the previous iteration, second iteration, due to its minimum distance, or level 7. Okay. So we can say that at level 7, for distance 7, we are having 3 clusters, 7, 10, 20, and 28 and 35. Hope this is clear. Now in third iteration, again the step is repeated, as it is single linkage approach. The minimum distance will be taken, 7 and 10, 20 will be 10, and the minimum distance between 20 and 28, 35 cluster number 3 will be 8. Right? 20 and distance between 20 and 28 is 8, and the distance between 20 and 35 is 15. So the minimum distance will be taken, that is 8. So hope it is clear from the example, that is minimum distance is 8. So at the end of third iteration, 8 is the minimum criterion, minimum distance. And so you can see here the new clusters are 7, 10, 20 will be merged with this cluster, 20, 28, and 35. Okay, so eventually the distance is 10, and after this step, all the data points will be clustered. So we can, what is the impact of this doing? What is the impact of doing this, Agnes? We can identify at level 5, at certain levels, at level 7, can see here at level 7 or distance 7, 3 clusters are formed. At level 3 or distance 3, level 1, can see the 4 clusters are formed. So based on certain distance or based on certain level, you can obtain different kinds of shapes. So this is particularly represented as the dendrogram that I will show in the next slide. And one more example I would like to show here, that is a complete linkage approach. The second approach for doing Agnes is you can also consider the complete linkage approach. Complete linkage means I will explain the example. The 5 data points are first one will be sorted in ascending order. The distance will be found out the first end of the first iteration, that is 3. Distance between 7 and 10 is 3. Distance between 10 and 20 is 10. Distance between 20 and 28 is 8. 28 and 35 is 7. So can find that minimum distance is 3. Right. So it is merged. 7 and 10 is merged based on the minimum distance criterion 20, 28, 35. So at distance at level 1 or distance 3, 4 clusters are obtained. Now we want to find out the distance between 7, 10 with 20. You can see here that maximum distance is taken here. The complete linkage means the maximum distance will be taken, considered here. The maximum distance is the distance between 7 and 20, that is 13. The distance between 10 and 20 is 10 only. That we considered in the single linkage approach, the minimum distance, right? So in the case of complete linkage approach, the maximum distance will be taken. So 13 will be taken as the distance between these two clusters. 20 and 22 will 28, 8, 28 and 35, 7. So at the end of second iteration, the new clusters are, what is the minimum distance here? 7. Right. So at the end of the second iteration, 7, 10 will be the same cluster 1, 20 will be cluster number 2, and 28 and 35, they will be clustered to form the third cluster. Hope this is clear. Now, that's the end of the second iteration. So now you can see how in the case of complete linkage, how the distance is found out. Maximum will be taken. 7 and 10, 20, the maximum distance is 13, and 20, and you can see here the distance between 20 and 28 is 8, and the distance between 20 and the 35 is 15. So as I mentioned, we are employing linkage, complete linkage here. So maximum distance will be taken. The 20 and 35 is the maximum. Then 15 will be taken here. Here, the minimum distance will be 13. So here 7, 10, 20 will be merged, and 28 and 35 will be continued as a single link cluster. So at level, you can see here at level 1, level 2, level 3, right? At level 3 or at distance 13, 2 clusters are formed. You can see here, level 1, level 2, level 3. At level 3, different kinds of different type of 2 clusters are formed at distance 10 only. You can see at distance 8 only. Here level 3 means distance is 13. So that's the difference between single linkage and complete linkage approaches. Again, we can represent this the distance and level in a diagram that is known as, commonly referred to as dendrogram representation. So dendrogram representation for hierarchy clusters of data objects A, B, C, D are shown here. That is at level, for example, if you are using Diana from bottom, top down approach. Sorry, this is an example Agnes itself. The 5 data points are merged. You can see here the merging criteria here. At level 1, A and B are merged here at 0.8. At level 2, D and E are merged here. That is at the distance between 0.7, nearly equivalent to 0.7. At level 3, C, D, E, they are merged here. Level 0.4 or distance 3, level 3 or distance 0.4. At level 4, all the data points A, B, C, D, E are merged. So that is nearly 0.16. At 0.16 distance, all the data points A, B, C, D, E are merged here. So this is the common output that we receive. That is a common outcome that we receive from the hierarchically based algorithms, that is known as dendrogram representations. It's very useful for understanding. Okay, again, clustering these connections, it will give you more insight about the data set. Another example of how dendrograms are represented. So that's all about the hierarchical based clustering algorithm. We have covered 2 algorithms. The first one is partitioning based algorithm, where we we evaluated the working of k-means. The second one is hierarchically based algorithm, where we evaluated the working of Diana and Agnes. So we evaluated the examples, the Agnes. There is two approaches. There is single linkage as well as complete linkage. How the output, how the output will give various insights about the data set. So what are the difficulty with the hierarchical? The second algorithm, that is hierarchical clustering. So once a group of objects is merged or split, the process at the next step will operate on the newly generated clusters. It means we cannot backtrack. Back propagation, all these techniques we cannot work. So once a decision is taken, that is in the case of Agnes, once a merge is done, once the next step, no, the optimal decision will be based upon the previous decisions. The next optimal decision will be based upon the previous decision already made, and it cannot, if you want, and again, if some other better decisions are obtained later, if you know, if you, it cannot be back techniques like back propagation will not work here. So thus, once merger split decisions are taken, if it will not be backtracked. If not chosen well at some step, it may lead to low quality clusters. So the level, no, the level, the previously mentioned, the level at which level you want to merge, that decision you should properly take, you properly consider. The method does not scale well, so it is not advisable for big data analytics. So if you are having a huge number of rows, it will consume a huge amount of memory space as well as processing capabilities are required. So it's not recommended for big data analytics. Chameleon is one of the hierarchical based algorithm for using dynamic modeling. In this one, in Chameleon, cluster similarity is assessed based on how well connected objects are within a cluster and on the proximity of clusters. You can see here data set is given. All the data points after the first iteration, the algorithm construct a sparse graph. All the data points will be based on the based on the proximity or based on the neighborhood. All the points will be connected using the k nearest neighbor graph. Okay, so a sparse graph will be obtained in the first iteration, and then the end of the first iteration, partitioning will be applied. Some partition criterion will be applied to the this sparse graph, and we can obtain the partitions like this. Okay, and these are all individual clusters, and these clusters will be based on some merging criterion. They will be merged to form meaningful clusters. So this is an example for chameleon. So they employ dynamic modeling. That is, first of all, in the first step, they can create a sparse graph by connecting all the data points given in the input based on the proximity and partition it. Okay, not by partition, and merging will be happening at the end of the first iteration based on some merging criteria. So the knowledge about the domain knowledge is very crucial in this dynamic modeling aspects, because interconnectivity is taken for merging part for the step merge partition step. So next one is DB scan, and so you'll see one video here. And this is the third kind of clustering we are going to see here. That is DB scan. As I mentioned in the first two examples, the first example is specifically the partitioning based method. They are employing the mean value, right? The center value. So again, the center value will be affected by some malicious or some column value which was mistakenly entered by the researcher or some other person by entering the value. Okay, so that is those values are called outliers. Now, to find out the outliers or noise points, DB scan algorithms are effectively used to find out such points, noise points. So unlike k-means and k-medoids, the desired number of we are mentioning that, right, in the case of k-means or k-medoids, we are mentioning the number, what the number of cluster we require. The case of cluster, again, and one of the drawback with the hierarchical and the partitioning approach is that there are number of iterations, n number of iterations will be happening. So for the first drawback, for the first advantage of DB scan is that it takes care of these noise or outliers, and it also takes care. It will be performing this. It will the execution. No, it will complete the execution in one phase. In one go itself, it will complete the implementation phase. So all the points. So here you can see here 5 data points are shown in this video, in this figure, that is P1, P2, P3, P4 and P5. Okay, so center point, you can see the P1 is a center point here, and hello. Okay, so as I mentioned in the beginning, for proper functioning of DB scan algorithms, we need to mention, you need to you need to mention along with the data points, it should also mention two things. That is minimum points. What is the minimum point do you require? That is the density. Okay, what kind of density you are expecting? For example, and along with the radius, you need to mention the radius also. That is threshold value epsilon. You need to mention the radius, and that is here the radius is shown logically. Some one radius is shown two. There is 2 units around P1 is drawn here, and you can also mention the number of minimum points you expect. That is the density. Okay, the density of the algorithm means the number of points that you expect within a particular unit of radius. That's the density. So these two things you should mention. So you can obtain the implementation of this Python. No, you can obtain the R programming as well as Python programming code. So once you download these codes, if you're connected with your dataset, you need to mention these two. You can check the input variables like epsilon and minimum points, and you need to change it based on the domain. Okay, I'm directly going to the data. So 12 data points are shown here. Okay, the first step is skipped because it takes some time, and 12 points, the distance between the 12 points are shown here, and here it is 12 points. Now the distance between P1, the 12 P1 and P10, the distance between P2 and P1, the distance shown here is Euclidean distance only. Okay, the distance is Euclidean distance only, and the distance between P3 and P1 is 2.83. The distance between P4 and P1 is 4.24. Likewise, the distance between P12 with P1 is shown here. The second step, the distance between P2, no, all these points will with the P12 will be found out. Okay, now, so at the end of the first iteration, the distance between these two the points will be found out. At the end of the first iteration, as I mentioned before, at the beginning of algorithm, you will be mentioning epsilon. Epsilon means that the minimum radius you are expecting, the minimum radius or the neighborhood you are expecting. Minimum points means the density. You are expecting that within that epsilon radius, you are expecting 4 points. Okay, you are setting some quality standards for your algorithm. I want 4 points for it. That is the density aspect. Now, so we are going to check at this is the output of first iteration. Okay, so at the end of the first iteration, these two are the criteria for selecting the cluster for DB scan. That is the P1 evaluates P1 all these points will evaluate the distance with other points. These 2 points will be considered. Okay, we can check it. That is epsilon will be mainly chosen. The distance from P1, can check here the minimum distance. It is showing minimum distance. Now as you can see here, there is points with below this point, the maximum. So epsilon means the maximum radius you are expecting. Okay, so not the minimum. Sorry, I mentioned minimum. Epsilon means the maximum radius you are expecting. Within that, you are expecting a density of 4. So P1 means the distance P1 with all of the distance is shown here. You can see here P10, the distance is below 1.9, right? The distance from P1 and P10 is only 1.41, and you can see, can check the 1.41 now. Again 1.41, you can see here P2 is also within the radius 1.9. So we can write P1 within the radius 1.9 epsilon. 2 points are nearest. Okay, 2 points are obtained, that is P2 and P. We can say that with the proximity, the neighborhood of P1, 2 points are obtained, P2 and P12, based on the distance, maximum distance 1.9. You can see here only 1.41, P10 and P2 are showing the proximity within the distance radius 1.9. P2, you can see here P2, we are checking with the epsilon value 1.9. P11 is showing the proximity within the 1.9 below value. Again, one more value P3, 1.41. Okay, so we can write down here P2, the nearest points will be P1, P3 and P11. These 3 points are showing close to P2 within the distance is below 1.9. Likewise, P3 is having close to P2 and P4. P4 is close to P3 and P5 within the epsilon value. So within these values, no, the 12 in the clusters shown here, the 12 are evaluated based on epsilon value 1.9. Around so at the end of the first iteration, this is the output. The points from each point, an epsilon radius will be drawn logically, and they will evaluate what is the number of points residing in that particular or within that neighborhood. You can see here, as I said, another condition, minimum points 4. So at the end of the first iteration, I expect 4 points in a particular cluster. These 12 points can be considered as partial clusters, and I'm setting a strict condition that I want 4 density. The density should be 4 to classify as a cluster. Okay, you can see here P1. P1 is in the P1's proximity of below epsilon. It is having 3 points only, so it doesn't qualify as a cluster. And you can check here the next cluster P2. It is having 4 points, right? Including P2, it is having 4 points. P2, P1, P3, P11, right? So these 4 points form a single cluster because it satisfies my strict criteria, that is minimum 0.4. That is the density. The third one doesn't qualify. It contains 3 points only. The fourth one, 3 points only. The fifth one, P5, again, it qualifies as a cluster because it contains 5 points around its proximity, right? It satisfies the density criteria, strict criterion. So P5 again, it forms a cluster, so core point. So these points, that satisfies the minimum these two criteria are called core points. P2 is a core point, P5 is a core point. You can see here P11 also satisfies this, the strict criterion, right? So P11 is also a core point. So those points which classify these two conditions are called core points. All other points will be considered as noise points. So I'm going to the next phase of density based scan algorithm. The second half of the algorithm. In this one, you can see here. That is the first one. This is the output. The P1 is noise, considered as noise. P2 is considered as core. Hope it is understood, right? Because P2 classified, because around P2 with the minimum radius, with the maximum radius 1.9, we are able to find 4 points, including itself. You can see here P2 is satisfied as a 4 point here. All other points are considered as noise points here initially. You can see a P5 is considered as a core point, and P11 is also considered as a core point here. The final step of this DB scan algorithm is that some of the noise points will be converted to border points. Now, how it is happening? One more condition is applied. That is, so at the end of the DB scan algorithm, some of the noise points in the first half of the algorithm will be converted to border points. The condition is simple. The simple condition is if a particular noise point is density reachable from a core point, it is a border point. Again, repeat the rule. If at the end of the first half, all the points will be converted. The qualified points will be converted to core point, and all of the points will be represented as noise points. And at the end of the DB scan algorithm, some of the noise points. What is the importance of noise point? It will not be considered for clustering analysis, right? But not all the points will be, that is not core point, will be considered as outliers. Some of the points will be converted to border points, and they will be considered. Border points will be considered. Now, how to find out the simple rule is applied? If a noise point is density reachable from a core point, it is considered as a border point. Now we can check here P1. P1 is a noise point. You can check here. You can check here the P1. It is reachable to. You can see here within its proximity P2 is there. Right, P2 is a core point, so it cannot be considered as a noise point. It will be considered as a border point. So status will be changed from noise to border. P3 also same here. P3, take P3. You can check here the within P3's proximity P2 region. A core point is the P2, right? So it will be considered as a border point. P4 also, P4 you can check here P4, P5, right? P5 is a core point, so it will be considered as a border point. P likewise P6, P7, P8, and P9 you can check P9. P9 only P12 is there within its proximity radius epsilon. So P12 is not a core point, is a noise point, so it will be discarded. It will be considered as a core outlier. So at the end of the DB scan algorithm, the noise point, the outlier point P9 is identified. That is a very important outcome of DB scan algorithm. How noise point is this? So this is an example of how noise points are evaluated. The first half of DB scan algorithm, the distance will be found out between various objects, and these two conditions are applied: the minimum distance, that is maximum distance, that is epsilon, and the minimum points, the density that we expect. But these things we can change it, and we can employ the trial and error approach. So then the second half of the algorithm, we can obtain the points will be converted to the core point and noise point. And some of the noise points, when we apply a symbol rule, that is, if a noise point is density reachable from a core point, it is considered as border point. When that symbol rule is applied, some of the points that are already noise, considered as noise, will be converted to border. Again, it's a strict criterion. We want to find out the actual noise point. Okay, so we have found out the noise point, that is P9. So this is how DB scan evaluates, find out the noise outliers. So one more algorithm is the sting algorithm, and I just have a quick overview of sting algorithm. That is a fourth classification. That is grid-based approach. 5 minutes I'm going to cover this portion. And so far we have seen partitioning method. That is why we evaluated a few problems related to k-means, right? And one-dimensional, two-dimensional examples. In the case of a hierarchical method, we also we evaluated few examples using single linkage and complete linkage approach. And again, the third one, we have seen a problem related to DB scan. We have a number of algorithms for even for density-based methods also. And one of the popular method for finding the outlier is DB scan. And the last one that we're going to cover in this topic is grid-based method. And one of the popular example for grid-based method is STING, statistical information approach to spatial data mining. So this is the approach in which we convert space into a finite number of cells that form a grid structure on which all the operations for clustering is performed. And I'm directly going to an example here. So it's like we can visualize the working of Google Maps. So when you're in the top layer, when you're opening Google Maps initially, and if you want to zoom into your particular place, the point of location, no, you will be zooming. Like you will be I think you will be performing your 5 or 6 steps only. When you perform, when you roll over, when we perform the mouse rollover or the zooming operations, in 5 steps, n number of steps, you will be reaching your particular destination, the place where you want to. If you want to visualize a state, the number of steps will be less. If you want to visualize the details like a particular road or a particular shop, the number of steps you need to go deeper, right? So the more layers to top bottom layers should be evaluated. So here in this approach, the rows or transactions or data points will be clustered based on grid format. Okay, so in the ith layer you will be so that from the ith layer you will be obtaining this top level statistical details only. If you're in the first layer, the topmost layer, you will be getting statistical details of your data, and the top level view only. You'll be getting the big picture only. Now, if you are in the I minus 1th layer, that is, if there are 10 layers, if you are in the 10th layer, you will be obtaining you will be getting the big picture of your data only. Now, that is a grid structure. Now, if you're going to the 9th layer, the 10th layer will be further divided into 4. The 10th layer will be further divided into 4 child layers. Okay, and then the 9th layer, suppose in an example, there are 10th layer. 10th layer will be divided into 4 child layers. And in the 9th layer, you will be having 4 layers. You will be divided into 4. Again, so again, you will be getting a view, and then that particular layer only, statistical informations of those 4 layers, consolidated views only. Now, if you're selecting at the layer 9, if you're selecting a particular cell and you're further zooming into layer 8, no, you're coming down to layer 8. Again, that particular cell you choose will be further divided into 4. So when you go deeper, when you go from top to bottom, each cell will be divided into 4 more cells. Likewise, in the last layer or the leaf layer, you will be obtaining the actual data, the statistical details about the actual data points. Okay, so for each cell in each layer, we have attribute independent parameters, that is the number of records in the cell. Attribute dependent parameter also with that. We are assuming that our attribute values are real numbers. So each cell means the as I mentioned, the statistical details of each cell is represented here. So in the top level views, you will be getting 2 levels of attribute details, attribute independent and attribute dependent parameters. For each attribute, sorry. So spatial areas divided into rectangle cells. So here in the grid-based approach, the spatial area is divided into rectangular cells using latitude and longitude, and each cell forms a hierarchical structure. This means that each cell at a higher level is further partitioned to 4 smaller cells in the lower layer. In other words, each cell at the ith level, except the level leaves, has 4 children in the I+1 level. The union of 4 children cells will give back the parent cell in the level above them. Likewise. Okay, so this is all the representation of hierarchical structure for string clustering. So these kind of structuring, these kind of clustering algorithms were basically used for, it will be looking like this. So grid-based structure, even though you need to zoom in from the nth layer to the bottom leaf layer. So it's basically for clustering spatial data. And this is also very, these kinds of algorithms are very useful for big data analytics also, because the algorithm performs the execution complexity. The complexity of this algorithm is only big O of n log n. So it works very faster compared to other algorithms when you are dealing with big data analytics. Okay, so that's all about clustering. And so thank you all for patiently hearing my session.